Hello class, time to look at some circles and composite shapes and regular polygons as well. So here's our warm-up. We need to find the area of the figure. We have a trapezoid to start and we are given our base, both bases and the height. That makes our lives much easier. So all we have to do is use our formula. Area is equal to 1/2 times the height times base 1 plus base 2. So that's 1/2. Our height is 5 times our base of 10 plus our base of 18. So when you multiply all that out, we got 1/2 times 5 times 28. And now we can multiply 5 times 14, which is 70. Okay. Now for number 2, we have a rhombus. We know that because it is a rhombus, the diagonals are what we're going to use. And that means both diagonals are bisecting each other. So since we have half of each diagonal, the other side is 9 for one of them, for the shorter one. The other side is 13 for the longer one. So that means we have D1 is 9 plus 9, or 18. D2 is 13 plus 13, 26. So our area is 1/2 D1 times D2. So 1/2 of 18 times 26. So that's 9 times 26, which comes out to be 234. Okay? So, vocab for the day, sector of a circle, segment of a circle, center of a regular polygon, radius of a regular polygon, apothem, central angle of a regular polygon, and composite figure. So, area of a circle, hopefully you've heard this before, is the area is equal to pi r squared. So pi, 3.14 if you round it, times the radius squared. So here's a manufacturing example. An outdoor accessories company manufactures circular covers for outdoor umbrellas. If the cover is 8 inches longer than the umbrella on each side, we need to find the area of the cover in square inches. So in order to find area, it's pi r squared. So we have that the inner diameter of the umbrella itself is 72. So we take that 72 and divide it by 2. That's 36. And we add the 8. Because that way we get a total total radius. So that is 44. There's our radius. Okay, now we're going to plug that in pi r squared. So pi times 44 squared. So pi times 44 squared comes out to be 1936. And if you want, I like to leave them as stuff like that, so 1936 pi, but in this class we're not going to do that. So we're going to multiply the two together, pi times 1936. That comes out to be 6,700, or not 6,700, 6,079.04 square inches. Okay? Our next example, very similar. It's not a umbrella now. Now it's a swimming pool cover. It's for an above ground pool. It's 1 foot longer than the pool on each side. We need to find the area of the cover. So again, we're going to take our diameter of the pool itself, the 18 feet, and divide it by 2. That'll give us the radius of the pool itself. So 9. Then we're going to add the 1 foot on either side. You don't have to add both sides, just the one. So our radius is 10. So our area, pi r squared, is pi times 10 squared. 10 squared is 100. So 100 pi, or 314.2 feet squared. And that is our answer C here. Here we have to find the radius of a circle with an area of 58 square inches. So we know our area, now we need to find the radius. So we're going to work backwards. So 58 is our area. We know area is equal to pi r squared. So 58 is equal to pi r squared. Divide both sides by pi. That comes out to be about 18.47. Now we don't want to round yet, but for writing's sake, I'm going to round. So then we square root both sides. R comes out to be about 4.297 inches. So about 4.3 inches if you round to the whatever you want to. It doesn't tell us what to round to. It really should, since this is dealing with pi. There's going to be decimals, but however you want to round it. I like to go to 3 decimal places. Sometimes I go to 2. Don't really like to go to only 1, though. All right. Our next one here, same idea. Want to find the radius. We are given the area. So our area now is 45. Equal to pi r squared. Again, we divide by pi. So r squared is equal to 45 over pi. I'm going to leave the pi in this time for now. Square root both sides. So r is equal, comes out to about 3.785 inches, which would round to 3.8 inches. So that means our answer should be A. Alright, so now we're looking at area of a sector of a circle. So the ratio of the area A of a sector to the area of the whole circle, pi r squared, is equal to the ratio of the degree measure of the intercepted arc X to 360. So basically whatever angle is making that sector is our X over 360. So area is equal to X over 360 times pi r squared. Alright? So we want to find the area of one slice to the nearest hundredth here. Now we're talking about a piece of pi. So first we need to know what our X is, and we are not given that. But we are given that it's cut into 10 congruent slices. So that means that our 360 is divided by 10 to get us 36 degrees. So 36 degrees is our angle of our arc for the sector, or angle of our sector, sorry, of our arc. So our area is equal to 36 over 360 times pi. Our diameter is 9, so our radius is half of that, 4.5 squared. So when we multiply all this out, I'm not going to piece by piece it because there's so much going on here. Our area comes out to be 6.362 inches squared. Okay, just be careful when you type that in the calculator because you want to make sure that the pi, our squared part, is separated from the fraction. Otherwise, when you type it in Desmos, if you're typing it straight up, it's going to think you're multiplying the 360 by pi r squared, not the whole thing by pi r squared. Okay, so this next one gets into a bit more complicated of a problem. So for one, we just want to label everything. Okay, so our center for the circle here is x. The radius I guess it's the center of the polygon, and the circle, so x is that. The radius of the polygon is from r to x, you can use that, or x to q, or either way, you can rewrite it however you want. So, or no, yeah, sorry, xr or xq, either one works. You can keep going if you want to, you can do xp, but we're only given those two, so we're not going to write any more than that. We also have to find an apothem, and one of those is given to us as xn. And then our central angle is angle RXQ. And the measure of that angle, you take 360 and you divide it by however many sides of the pentagon there are. So there are 5 sides to a pentagon. So 360 divided by 5 gets you 72 degrees. So there's all the things it wanted us to find. So now this next one is a bit more complicated. So we're given that this is a regular hexagon. Side length is 3. So the nice thing here is that a hexagon splits into 6 equilateral triangles. Okay? So really, because the way we know that is that 360 divided by 6 is 60. So that's the central angle, and we also know because that's our central angle, the other two angles split those angles they're coming from in half. The diameter, I guess, of a hexagon, or any of these, any even numbered regular hexagon, a diameter would go from angle to angle, cutting those angles in half. So we know that those are also going to be the same, so that means what's left out of the 180 from this triangle, from the 180 you take away the 60, you're left with 120. 120 divided by 2 is 60, so all angles are 60. So we have 6 equilateral triangles. So if we find the area of one of those, so remember, area of a triangle is base times height divided by 2, or 1/2 base times height. Either way works. Our apothem of this triangle is 1.7 feet, and that's our height of our triangle. So the base is 3 times 1.7 divided by 2. That comes out to be 5.1 divided by 2, and that is equal to 2.55. So now we're going to take that, so this is for the triangle, so the area for the hexagon is equal to the area of a triangle times 6. So 2.55 times 6, that comes out to be 15.3 square feet. Now, there is a formula that goes along with this. So, if you don't know that it's a regular hexagon, so with hexagons and all those ones that are nice and even, it's almost going to be always going to an equilateral triangle, but it doesn't always work out that way. So here, you give it a formula that works for any n-sided polygon. So however many sides, you find the perimeter, you multiply that times the apothem, and multiply that by 1/2. So here we have a hexagon. So again, we already know that that's an equilateral triangle, right? But we're only given the base, we're not given the apothem. So we need to figure out what the apothem is, and then use that, right? So because we know this is an equilateral triangle inside of here, that means that we have a 60-degree angle being cut in half by the apothem. So that's a 30, 60, 90 triangle. So there's a couple things we can do here. We know that the base is being cut in half, so this is 2.5 here. And our apothem is the longer leg of a 30, 60, 90 triangle, when the 2.5 is the short leg. So we just have to multiply our 2.5 short leg by square root 3. So 2.5 square root 3. We could do that, or we could just use the fact that we have one side, and we know that we have an equilateral triangle. In this case, this would only work with this case, that this is 5, this is 5. So we have an equilateral triangle, we have the leg, we have the hypotenuse, we can use Pythagorean theorem to find the apothem too. Either way, it works. 2.5 square root 3 is our apothem. So our area here is 1/2 A times the perimeter, right? Or 1/2 A times NS. So S is the number of the side length, N is the number of sides. So we have 1/2, our apothem is 2.5 square root 3. N is 6 in this case, and our side length is 5. So when we multiply all that together, we get that our area is 64.952 meters squared. It does say to round to the nearest tenth, so really 65.0 meters squared. All right, now this one makes it a bit more complicated because we are given that it is a pentagon now, or we're given a pentagon. So that means we don't have our equilateral triangle anymore. We have that, we know our angle inside here is 72. It's being divided by 2, so that's 36 inside. That means this guy's 54. Doesn't really matter what that is, though, because we know that 36, we can use that and sine and cosine to get our legs of our triangle, now that since we're also given our hypotenuse. So I'm going to label these as our S and L. So our sine of 36 is equal to S over 9. So S is equal to 9 times sine of 36. Cosine of 36 is equal to L over 9. So L is equal to 9 cosine of 36. Now, we're not going to calculate it yet. We're going to just use these in our calculations to make things nice and pretty at the end. Not really pretty, it's going to be a decimal, but no decimals to plug in, okay? No rounding early. So our area is equal to 1/2 our apothem, which we know now is our L. So our apothem here is L. And we need to multiply that times our perimeter, 1/2 r apothem times ns. In this case, n is 5. S is not our S we found already. S is equal to 2 times our side length. So, getting a little bit confused. I'm going to mark these with 1 here, so you know that that's part of the entire side, since we basically found half of the entire side length. So, our overall formula here, 1/2. The apothem is L, so that's 9 cosine of 36 times our 5 times 2 times 9 sine of 36. Lots going on there. But if you plug that directly into the calculator, your area will come out to be 192 point, and it rounds to the nearest 10th.6 centimeters squared. Alright, so we got 2 more examples and then an exit ticket. So our next example here is our first composite figure. So what we need to do, you can kind of see there's a rectangle in the middle, right? So I'm going to label everything. So we got our rectangle, we got a triangle, and we got a circle, right? The circle is cut in half on the ends of the rectangle, right? So 1/2 of a circle on either side. So basically we have a full circle. So we're going to find area of a rectangle, which is length times width, so 16 times 32. And that comes out to be 512, in this case, square feet. And we're going to find the area of a triangle. So in this case, our height is 15. Our base is the 32 still. And we're dividing that by 2. So that comes out to be 240 square feet. And then for the area of the circle is the one that's going to give us some decimals. Our radius for the circle is half of the 16 height or length of the triangle, not triangle, rectangle. So it's going to be 8. So 8 squared 64. 64 times pi gets you 201.06193. Didn't round really at all, just gave you what my calculator told me. And now we just need to add. So the area total is equal to all these added together, comes out to be 953.06 feet squared. Alright, so we got one more composite figure. This one's a little bit easier. No combinations of shapes, it's just 2 rectangles. So here we just need to find the area of the shaded area, and so we're going to find the area of the entire rectangle, subtract the area of the non-shaded rectangle, and we'll get our answer. So first off, our length for the large rectangle is going to be the 25 plus the 100 plus the 25 on the other side. Doesn't really say that that's 25, but it's pretty much assumed that it is. So that comes out to be 150. Our width for the large triangle, or large rectangle, sorry, is 25 plus 20 plus 25, so 70. Our length for the small triangle is 100, and the width for the small triangle is 20. So our area for the large triangle is 150 times 70. And that comes out to be 10,500. The area for the small rectangle is 100 times 20. So 2,000. And the area we were looking for is the area of the large minus the area of the small. So 10,500 minus 2,000. So 8,500 square feet. All right. There's your exit ticket. We'll see you next time.